In this section, we're going to look at preparing and reacting carboxylic acids. So a couple of these reactions, these oxidation reactions, we've actually already covered before. So if you have a primary or secondary alkyl benzene, so if we have a benzene ring with a primary or a secondary group, an alkyl group on it, we can use KMNO4. And this will actually cleave this off and turn this into a carboxylic acid. Typically this is done in water with some heat, delta or just the word heat, and what we end up with is the carboxylic acid. And when we learned this before, we talked about how we're not actually going to cover the mechanism of this, and we're actually not going to cover the mechanism of it here as well. But essentially, primary and secondary alkyl benzenes, we can cleave these off. Another oxidation product that we've learned is alcohols and aldehydes. So if we have C double bond O bond H bond R, or even R bond C bond OH, so if we have either the aldehyde or the primary alcohol, we can oxidize these things. And a typical oxidizing agent would be something like CrO3. CrO3. In this case, we get the carboxylic acid, R bond C double bond O bond OH. And in this case, we don't stop at the aldehyde. You can't get the single oxidation product, like with Des-Martin, using CrO3. This is just going to go to completion. Basically, you oxidize this to the aldehyde the first time, and then you oxidize it once again to the carboxylic acids. So we can turn aldehydes and alcohols into carboxylic acids through oxidation. These reactions we've covered before, but we didn't cover them in this chapter, so they're kind of review. There's a couple of other things we can do in order to find or make carboxylic acids. And one of them involves a nucleophilic substitution reaction. So if we have something like this, a C bond Cl bond H bond CH3, all right, I move this up, it needs to be a primary or secondary halide, alkyl halide, all right, but it has to be primary or secondary. If we use NaCN, sodium cyanide, a nasty chemical, the Cn minus can actually undergo an SN2 reaction here. So this comes in, you get the transition state where this is coming out and this is going in, and then this continues to come in and kick this out, and it's an SN2 mechanism. And what you end up with is the nitrile. So we end up with, I'm going to write it this way, C triple bond N, or just Cn. The CH3 goes along for the ride, and the H goes along for the ride. And then we would get, in this case, as the byproduct, NaCl, because the Cl comes off, and there's a sodium that was originally with this cyanide. Now, if we use this nitrile, we can actually turn this into a carboxylic acid. And in just a later section of this chapter, we'll actually cover the mechanism of this. But for right now, if we add NaOH, strong base, and water, followed by acid, H3O+, we can actually turn this right here into a carboxylic acid. And again, we will show that mechanism a little bit later on in this chapter. No sense to show it twice when we're doing videos, so you can watch as many times as you want. So this is basically how this reaction is going. So it allows us to go from alkyl halides to carboxylic acids through a nitrile using sodium cyanide, which again is a nasty chemical. The next thing we can do is actually use Grignard reagents. Remember that Grignard reagents are generally forming alcohols from aldehydes and ketones. But there is a special case when we use carbon dioxide, and often the carbon dioxide is used in the form of dry ice. So if you take phenylmagnesium bromide, a Grignard reagent, and you add carbon dioxide to it, again, usually in the form of dry ice, and then in step 2, we add H3O+, all right, so 1 is carbon dioxide. I can put 1 carbon dioxide, or I'm just going to write carbon dioxide there. You can actually make benzoic acid this way, like so. All right, so how is this working? So this one, we can actually show the mechanism. The other ones, we've either shown the mechanism in the past, or we'll be showing the mechanism in the future, or in the case of the oxidation ones, we basically aren't showing the mechanisms of these oxidations. Well, if we look at this one, we have here MgBr. And here we have C double bond O, double bond O. Now, a big hint that this is going to attack the carbon is that the carbon ended up attached. We don't end up attaching the oxygen. But why does this attack the carbon? Well, I could write a resonance form of carbon dioxide where we have the minus charge, these electrons come up onto oxygen, and a plus charge on carbon. Said another way, this carbon is partially positive. This Grignard reagent, if you remember, makes this carbon atom partially negative. So this partially negative carbon attacks this partially positive oxygen. Again, in some books they'll show the MgBr helping to stabilize these charges and whatnot. I'm going to just simplify it here. And what we end up with is this coming in and this going up. And what we get is the benzene ring, bond C, bond O. Now this comes up with a minus charge, double bond O. And we have the MgBr as simply the counter ion here. We then add H3O+. And I'm going to draw the carboxylic acid upside down because I did show this going up instead of this going down, just so it's clear. All right. And here, this H3O+, this grabs a proton, and we get C bond OH, double bond O. Again, this is upside down. Usually you write it this way and not this way, but they're the same thing, okay? And in three-dimensional space, there is no right side up or upside down, really. It's just this is a traditional way of writing it. But what you can see is this is a special case where we don't actually get the alcohol by using carbon dioxide. Instead, we use the Grignard in order to get the carboxylic acid because the carbon already came with a C double bond O, as opposed to if it was an aldehyde or a ketone, where it came with some H's or some carbon container things or some combination of the two. So that is basically how that reaction is going. Now that we've looked at the formation of carboxylic acids using nitriles, using Grignards, using oxidations of primary alcohols or aldehydes, or the oxidation of primary or secondary alkylbenzenes, what we want to look at is a reaction of these carboxylic acids. And the specific reaction that we want to look at is the reduction. All right. So what we have here is we have a carboxylic acid, which I'm going to draw as R bond C double bond O bond OH. All right. And you'll remember that we have two popular reducing agents, sodium borohydride and lithium aluminum hydride. And in this case, we're using the stronger one, lithium aluminum hydride. And you'll remember that lithium aluminum hydride is an aluminum bonded to 4 hydrogens, giving aluminum a minus charge. And what happens here is this acts as a source of H minus. The lithium is just a counter ion sitting over here with a positive charge. So this acts as a source of H minus. This comes in here and kicks this up. And in your book, they show the aluminum basically stabilizing this charge. So you could have aluminum sitting here first, or you could have this kind of come in and kick this up, and then aluminum is sitting here. I don't know which happens. Probably the aluminum stabilizes the charge, stabilizes the partially positive charge on the carbon, but that's not super important. So we get R bond C bond O, now with a minus charge, somehow coordinated to an aluminum R3. All right, the first time through, it might be 3 H's, but then the second time through, you may have some byproducts here, like aluminum hydroxides. Again, not super important. We're just going to call it AlR3, is kind of stabilizing this negative charge. All right, we have the OH, there's 2 lone pairs here, Okay, and now we have an H. Well, this molecule doesn't really like to have both of these oxygens attached to this bond. And because we have this stabilization of the aluminum, we could go through and protonate this a few times and turn it into water, and then water is a good leaving group, and then it could come off. Or we're going to say that we have some kind of stabilization with the aluminum. So this comes in and kicks this out. Does the H come first? Does it get kicked out first? My guess is this H comes in and then this gets kicked out. But again, it's not super important for how it's going. So what do we get? We get R bond C, double bond O, bond H. We now have a plus charge. Bond H. We're closer to the alcohol. But instead, what we have is we have a protonated alcohol. We have a protonated aldehyde in this case. So we have R bond C, double bond O, bond OH. So what can happen? Well, any kind of base, including something like water, can grab this proton and we can go here. And what we end up with is R bond C, double bond O, bond H. We now have the aldehyde. Well, this reaction mechanism you've actually seen before. And what happens is we have lithium aluminum hydride. So we have Al, H, 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 H. This is the source of H minus. This comes in, kicks this up. Now we're closer to the alcohol. We get R, bond C, bond H, bond another H, bond O minus. We add H3O plus. This grabs a proton, and we end up with R, bond C, bond H, bond H, bond OH. So this is the mechanism for the reduction of carboxylic acids. But we should probably write this as a general reaction so that it's a little bit more clear. So if we have R bond C double bond O bond OH, a carboxylic acid, and we use lithium aluminum hydride, all right, that should be an H, all right, then we can basically form the alcohol. R bond C bond H bond H bond OH. So we go from a carboxylic acid to a primary alcohol using a stronger oxidizing agent or reducing agent, like lithium aluminum hydride. So we've learned a few things. One reaction of carboxylic acids that we've learned is reduction. We also learned about the oxidation of primary and secondary alkyl benzenes using KMNO4, usually in the presence of water and heat, to form carboxylic acids. We looked at the oxidation using a strong oxidizing agent, CrO3, with aldehydes and primary alcohols to form carboxylic acids. We learned a new reaction where we do a nucleophilic substitution with sodium cyanide. We've seen that reaction a lot. This minus comes in, kicks this guy out, and cyanide replaces chloride. But then we learned a new reaction where if we add a sodium hydroxide, water, followed by H3O plus, we can actually turn the nitrile group into a carboxylic acid. Finally, we learned for synthesis of carboxylic acids that if we use a Grignard reagent and carbon dioxide followed by H3O plus, we get the carboxylic acid. And the final reaction that we looked at was actually the reaction of a carboxylic acid, which is reducing it using a stronger reducing agent like a lithium aluminum hydride to get it to go all the way to the alcohol. Note, it does not stop at the aldehyde, even though you saw the aldehyde in the reaction mechanism. So what I'd like to do at the end of this is kind of put this all together into one fairly complex question. So let's say we have something like this. We have a ring, some R group here, and we have CH2Br. And I would like to know two ways to get this to form over here. A ring, CH2, CH2, OH, like that. So, what is the difference between this molecule and this molecule? Well, there's a couple differences. One, this is an alcohol, and two, and in this one, it's an alkyl halide. The second major difference is the number of carbons. So we can't simply do a nucleophilic substitution reaction. If we just wanted to substitute this Br for an OH, we could do that. But that isn't going to work here because we actually have an extra carbon. So how are we going to add that extra carbon? Well, the one way we could do this is through a Grignard reagent. First, we want to add Mg, usually in ether, and we talked about this in a previous chapter, in the alcohol chapter specifically, and in the aldehyde and ketone chapter as well. So here we have R bonded to the ring, bonded to CH2 MgBr. Well, now we want to add this carbon, and we want to form this into a carboxylic acid. Well, how do we use Grignards to form carboxylic acids? I should have made this arrow a little bit longer, so I'm going to redo that. 1, we want to use CO2, and 2, we want to use H3O plus in order to protonate it. And what we end up with is R bond the ring, bond CH2, C double bond O, bond OH. We've now added our extra carbon. Now we have a carboxylic acid, but what we actually want is an alcohol. Well, luckily, that reaction is right here. How do we turn from a carboxylic acid into a primary alcohol? Reduction. And lithium aluminum hydride allows us to do that reduction. What is another way to get here? Another way to add this carbon? Well, we talked before about why a nucleophilic substitution of just OH wouldn't work. And the reason that it wouldn't work is because we have one carbon here and two carbons here. But what if we substituted it with something with an extra carbon? Specifically, what if we used NaCN? All right. When we do that, we get R bonded to the ring, bonded to CH2CN. All right. Now that we have that, we can turn that into a carboxylic acid. That is NaOH and water, followed by H3O plus. This then makes this into that same carboxylic acid that we have up here. R, the ring, CH2, C double bond O, bond OH. The last step is exactly the same. You need to use lithium aluminum hydride in order to reduce it to the primary alcohol. So there's two ways to get the exact same carboxylic acid, whether we go through Grignard with CO2 or we use sodium cyanide with NaOH, water, and H3O plus. In the next section, we will look at the reactions of nitriles, well, specifically the synthesis of nitriles, as well as some reactions of nitriles.